Okay, welcome. We're going to start a new lesson series, lesson 5. This will be on the partial F test. This probably is the most fundamental parts of this section, in that if you can kind of understand the partial F tests, the other tests seem a little easier. So today we're going to talk about setting up the null hypothesis, but before we do that, we have to go ahead and review what we've had before. Okay, so the big question again is, what predictors do we include in our linear multiple regression model? Again, we have multiple regression analysis. We're taking a model. In this case, we'll look at some other models later like logistic regression, but here we have beta naught plus beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon, where the mean of epsilon is 0 and the variance of epsilon is a standard constant. And remember, the error random variable follows a normal distribution, has a mean of 0, the standard deviation is constant, and is mutually independent at various points. That is, there's no pattern. There's a random scatter about 0, and if it doesn't, then we talked about earlier about transforming it. And we look at a probability plot of the residuals. We don't have to check the mean being 0 because that's automatic by least squares. And remember, least squares criterion is the least squares estimates are those values of the BIs, those are one of the estimate betas, that minimize the sum of the squares of the residuals. Summation of yi minus yi hat. The yi hat is your line, and there's a little picture of that. I think I chopped off the y hat there. Rats. Okay, so again, we're measuring variation statistics, the sum of squares totals, the sum of squares regression, plus the sum of squares error. The sum of square errors, the sum of the squares residuals. We want that to be a small percentage of the total variation, and the regression sum of squares is kind of a measurement of the explained variation. And then the coefficient of multiple determination of r squared is the sum of squares regression of the sum of squares total. The closer that percentage is to 1, the better our model in general explains, and it's closer to the plane or line that we're talking about. When the SSE is large, then that r squared is closer to 0, and we may not have as much faith in our model. Depends on what we want to do. So just remember that you can just keep throwing in predictors to inflate your r squared, and so it's not always the end-all be-all statistical measurement. It's a good measurement, but don't just trust it on its own. So we talked about what predictors should we use. The first one, the overall F test, would take any of them. And then, does a particular individual partial slope contribute? Then how? And that was our t-test. We looked at a specific one. And then, do some of the predictors explain the variability? How much? And that's what eventually we'll get to in the partial F test after we do a little review. Just in terms of what predictor variables to use, there are 3 approaches. The forward selection approach, keep adding an explanatory variable to see if it explains the response variable. Then you can use the overall statistic to determine. Then there's something called stepwise regression. Throw one in, see what happens, throw one out, throw one in a couple times, and just kind of go back and forth until you reach an equilibrium. And what we talked about was the backward elimination method, where we start with all the explanatory variables, calculate the t-test for each variable, and throw out the one with the largest p-value, and repeat this process until it's below a certain threshold. We just kind of said at 0.1 level, but you could have different variables. In all of these situations, you're trying to figure out, what is the purpose of my test? What am I trying to do? So for example, here's the overall test, looking at this particular test and we find out the sum of squared error is really quite small compared to the sum of squared regression. And we have a pretty high F value with low P value. So we could say, okay, with this overall test, at least one of these predictors help explain our response variable. Again, if the null hypothesis is true, the mean square regression, mean squared error will roughly be the same, and then we have the F test to kind of help explain that. The next question is, does a particular one contribute? That's where we look at the t value, and we can look at the model summary. Just remember that the t value and p value only measures it for when your null hypothesis is 0, and we did some examples when your beta I may not be 0. But in this case, we have a small p-value, so we would say, okay, in this case, the age does not contribute to the model. Notice we kind of have to make sure what situations we're in. A small p-value, hey, that's great. A small p-value in other places, no, we don't need this. So you just kind of have to keep track of all these tools. And so we'll just do another example of the backwards elimination method. So again, remove the highest predictive variable until all the p-values below some value to 10% is suggested. For example, what predicts hate crimes in 2016? This was from the website 538 from Nate Silver. He's sometimes known in political and sports circles. Here are all the predictors that were used. And we did the first regression. We threw out the largest one. That was the share of white poverty. We regressed again. And then we threw out the next one, the median household income. Do it again. It looks like 0.363. The share of voters who voted for Trump, throw out that one. Look at it again. It looks like share of unemployment, seasonal. And then we do it again. The share of the population that's within metro areas. And we looks like the share of non-white population. And so share of non-white citizens, throw that one out until we end up to the model to predict hate crimes, the share of population with just a high school diploma, and the Gini index. We might talk about the Gini index. That actually might incorporate all of the other predictors that were included there. But that's the process that we would go with the backwards elimination method. Well, now we have to go to actually testing what we did. So it's an informal process, and the partial F test is a way to test whether it's appropriate to throw the models out, throw those predictors out. So the partial F test, when we get to it in lesson 2, will the sum of squared errors reduce minus sum of squares over the full minus degrees of freedom reduced minus degrees of full, and all over the mean squared error of the full. We'll try to explain that in lesson 2. Today we're just trying to set up the null hypothesis. And sort of like Gideon again, does a group of some predictor variables contribute in any way to explain the variability in the response y? So we kind of looked at one variable. Well, suppose we have 3 or 4. We threw out 7 or 8 in that hate crime example. How do we know that we didn't make a mistake and that maybe they would contribute? So the key thing for us today in this particular video is how to set up the null hypothesis. So the original question, or the question addressed by the partial F test, is does a group of some predictor variables contribute in any way to explain the variability in the response y? So we start off with a model with lots of predictors. And so our question is, do any of those, like G plus 1 to K, do any of these help explain our linear model? If they don't, they're kind of dead weight and we should kind of get rid of them. So the verbal version of this is the predictors xg plus 1 to xk do not help explain the response y, versus the alternative hypothesis, at least one of those predictors does help explain the response y. Sometimes this is a nice way to write it. We'll give you 3 ways. You can decide which one you decide works the best. I kind of use all 3 at different places, just determining what I think communicates the most. So that's the first one, is the verbal version. The second version is the reduced versus the full model. So the null hypothesis is the model of y equals beta naught up to xg, and this is the model that we throw out the dead weight, or so we think it's dead weight, versus the full model, the alternative hypothesis y naught up to all of the k predictors, and that's our full model. So this is another way that we could represent the null and the alternative hypothesis. The third one, you just look at the coefficients alone. You say, okay, the null hypothesis is those last few variables are all 0, and the alternative hypothesis, at least one of those last few coefficients is non-zero. So each one of these 3 have different ways. They're all saying the same thing, and you can kind of review what you find in your course pack on page 145 to kind of help you out and kind of review them. So let's go to page 146. And remember, the question is, does a group of some predictor variables contribute in any way explain the variability in the response y? So the original blood-brain original model included tumor, loss, weight, days, time, treatment, and female. And from the backwards elimination model, again, which is just exploratory, it seems we can eliminate tumor, loss, weight, and days. And so we just need to use the formal statistical test to determine, yes, we can throw these out. So verbally, we would say the predictors tumor loss weight and days can be eliminated from the model containing time, treatment, and female. And the alternative hypothesis is at least one of those predictors, tumor loss weight and days, is needed in addition to the ones we were going to keep anyway, time, treatment, and female. So that's what we could say verbally. You could also say this as the reduced versus full model. So the null hypothesis that y is equal to beta naught plus beta time x1 beta treatment times x2 plus beta female times x3 plus epsilon. Or we might have the full model, beta naught plus beta time x1 plus beta treatment plus beta female plus beta tumor plus beta loss plus beta weight plus beta days plus epsilon, and that's the full model. And so that's what we could have if we wanted to write out this way, just in terms of the numbers. In some ways, if you have a pencil, this is kind of an easier way to do. Sometimes you have to type this in. It's a little more complicated. And then we have finally the coefficient version, is we say, okay, the null hypothesis is that, hey, beta tumor, beta loss, beta weight, beta days is 0. Oh, I should have put a colon after that 0. So I guess I got to make that change, make that correction here at the very end. Let's just kind of cross off this stuff right here. Okay, that's our null hypothesis. An alternative hypothesis is at least one of those is non-zero. And so it's a formal test, and this is after we've done our backwards elimination method, or maybe a forward selection or stepwise regression. We need to do a test. And say if the null hypothesis is key, you want to go back, because you're going to do a lot of things until then. You want to be able to refer back to what your null hypothesis and make the conclusion. Just as a note, for the partial F test, there'll be fewer predictors in the null hypothesis than in the alternative hypothesis. The alternative hypothesis will be the full version, so you're keeping all or most of the predictors. And the reduced model, you're just only taking in or keeping the ones that came from your backwards elimination model. Okay, there's going to be a slight diversion, but I kind of talked long enough. Again, review these notes and perhaps this video, and I'll see you in video 2 of lesson 5. Now I should say goodbye. Bye.